So now we have our definition, and it's a good definition. It does what we need it to. The problem is it doesn't do it very efficiently. It's hard to use for anything but really kind of the most relatively straightforward functions. So what we're going to do now, we're going to derive some theorems and some properties that are going to make actually calculating specific limits for specific functions a whole lot easier. Okay, so let's start with this one. The limit of x as x approaches a is a. All right, so first, just so we're clear, f of x is my function. So f of x equals x. And here's what I'm going to do. I'm going to say that for this function, if I pick delta equal to epsilon, I get what I need. All right, so let's see why. If the absolute value of x minus a is between delta and 0, then what? Well, look, f of x, that's equal to x, right? So I'm going to replace the x here with f of x. All right, this means that the absolute value of f of x minus a is less than delta. But look, delta, I picked my delta to be the same as your epsilon. So this is the same as the absolute value of x minus a is less than epsilon. So why don't you just take a second, think about what I did. I showed that if this is true for any x, then this must be true. And this means the limit of f of x as x approaches a is a. But remember, f of x, that was just x. So the limit as x approaches a of x equals a. And there's our first theorem, right? Pretty straightforward. Okay, so how about this one? The limit as x approaches a of a constant is a constant, the same constant. All right, well, look, I'm going to do the same thing, right? Here, you can pick delta to be anything you want it to be. It's not going to matter, right? I'm going to let delta equal 1, right? Then what happens? If the absolute value of x minus a is between delta and 0, what do we know about the absolute value of f of x minus c? Well, look, remember, that is the function. F of x is equal to c. Oh, well, wait a minute, put that in here. Replace the f of x with c, and we get the absolute value of c minus c, which is just 0. And that's always going to be less than epsilon because you have to pick the epsilon to be greater than 0. Right? So, there's our first two theorems. Okay? Now, so here I've got a list of properties, and I know it looks a little long, maybe a little intimidating, but if you stop and look at them, and we'll talk about them here for a minute, they really are saying some really kind of intuitive things. This second one here, for example. Right, this second one says if I have the limit of the sum of two functions, that's the same as the sum of the two limits. In other words, I could just take the limit of the first function, the limit of the second function, and add them together. And hopefully those two limits of the individual functions, those are going to be a little smaller, maybe a little easier to do. Right? This second one here, third one, excuse me, says the same thing, but it says it for products. The limit of the product of two functions is the product of the individual limits. Got the same thing here for division. And finally, exponents. Right? Instead of dealing with this this function here with a function of an exponent, I can just do the limit of the function and then raise that to the exponent. Okay, so this. Okay, so this is our first limit property, right? And I want to prove this. All right, so here's how I'm going to do this. First, let's start off by letting the limit of f of x as x approaches a equal L. I'm going to use my limit definition here because it's the only tool I have so far. So I kind of need to have that L because it's a big part of the definition. All right, now all epsilon delta proofs, they all start off this same way. Let epsilon be greater than 0. Okay, now I'm going to define a second epsilon. Let epsilon 2 equal the original epsilon divided by the absolute value of C. Now, I don't know what C is. Maybe this new epsilon is bigger, maybe it's smaller, I don't know. It doesn't matter. The definition says for any epsilon, including this one that I've just picked. Okay, now, let's go to the definition. For this epsilon, there exists a delta greater than 0 such that for every x where the absolute value is 0 less than the absolute value of x minus c is less than delta, we have the absolute value of f of x minus L is less than epsilon 2. Okay, I'm going to put this epsilon over c in there for that epsilon 2. F of the absolute value of f of x minus L is less than epsilon over the absolute value of c. All right, now let's multiply both sides by that absolute value. Right, let's move the absolute value of c over to the other side. This means the absolute value of c times the absolute value of f of x minus L is less than epsilon. And let's bring that absolute value of c inside the other absolute value. This means the absolute value of c times f of x minus c times L is less than epsilon. Okay, but wait a minute. This was what I needed, right? This was what I needed. This is telling me that sorry, got a little tongue-tied there. This is telling me that the limit of c f of x is equal to c times L. But wait a minute, come back up here. Come back up here. Remember what L equals. L is just that limit. So this is the limit. I left out the x approaches a there. The limit x approaches a, c f of x equals c times the limit x approaches a of f of x. And that's what I wanted to show. Right? There's my first property. Right, so let's see if we can do one more. Then I'll leave the rest of these as exercises for you. So I'm going to start this kind of the same way. I'm going to say let the limit as x approaches a of f of x equal L. And I'm going to let the limit as x approaches a of g of x equal m. All right, now I'm going to start the same way we started the last one. Let epsilon be greater than 0. Right, then, again, I'm going to use kind of the same trick. I'm going to immediately grab another epsilon. I'm going to say let epsilon 2 equal the original epsilon divided by 2. Okay. Now, this next part is just a little tedious. All I'm going to do is I'm going to pull out the definition, but I'm going to pull it out twice. I'm going to use it for each of these two L and M limits that I have here. All right, if the limit of f of x equals L, then there exists delta 1 greater than 0 such that for every x where the absolute value of x minus a is less than delta 1, we have the absolute value of f of x minus L is less than epsilon over 2. Okay, now I'm just going to say the same thing over again, right? I'm going to say the same thing over again, but with m, right? There exists delta 2 greater than 0. You got to be a little careful because the deltas may be different since the functions are different. There exists a delta greater than 0, delta 2, such that for every x where the absolute value of x minus a is less than delta 2, we have the absolute value of g of x minus m is less than epsilon over 2. And I'm getting a little sloppy with my definition here. It should be 0 less than, and over here it should be 0 less than as well. Okay, so now what? Then, let's see. If the absolute value of x minus a 0 is greater than, is less than the minimum of these two deltas, right? Then what do we have? Then the absolute value of f of x minus L is less than epsilon over 2, right? And the absolute value of g of x minus m is less than epsilon over 2, right? If it was true for a number, if it was true for delta 1 and delta 1 was the bigger of the two, then it's still going to be true if we pick if it's a smaller number, if we make the x open interval even smaller. Okay, now let's think about what this means. This means that the absolute value of f of x minus L plus the absolute value of g of x minus m must be less than epsilon over 2 plus epsilon over 2, which is just epsilon. Okay, excellent. Now, look here's the little trick, and you may not have seen this before. There's this thing. It's called the triangle inequality, right? The triangle inequality says the absolute value of x plus a is less than the absolute value of x plus the absolute value of a. You notice how that's what I've got here. I've got two absolute values being added together. Okay, so the triangle inequality says this is greater than the absolute value of f of x minus L plus the absolute value of g of x minus m. All right, now let me write that again, because all I care about are the two edges. The absolute value of f of x plus g of x minus L minus m is less than epsilon. Let me rewrite this just a little bit. Let me factor the minus 1 out here. This is the absolute value of f of x plus g of x minus L plus m is less than epsilon. And that's what I needed. What have I shown? I've shown that if x minus a is less than that delta, then f of x plus g of x minus L plus m is less than epsilon. So this means the limit as x approaches a of f of x plus g of x is L plus m. But what were L and m going all the way back here to the beginning? That's just the limit x approaches a of f of x plus the limit x approaches a of g of x. And that's what I wanted to show. Right, there's my second property. Okay, so I'll stop here. Right, I'll stop here with those. take a shot at proving the other ones. Right? The other ones, the addition one isn't the subtraction one. Try doing the subtraction one first. That one isn't so bad. Do not do an epsilon delta proof for the subtraction one. Think about how you can apply this property and the property we did on the previous slide. You can prove the difference one just using these two properties. Okay, so now that we've got these theorems in hand and these properties, now we're in a position where we can start to actually calculate limits, and we can do it very quickly, very efficiently. For a lot of functions, there's a lot we still have to talk about, right? But that's what we're going to do in the next section, in the next lecture. We're going to look at some specific examples, see how these theorems help us to actually find specific limits.